get reflected from a surface or from an endpoint, then they can either be inverted in phase by 180 degrees or not, right, depending on what's the boundary. Now today we will discuss what happens if you want to continue the wave motion. That is, like I said last time, that there is always going to be damping, right? There is always going to be damping in a real situation. Now if you still want the amplitude to remain high, then it's necessary that resonance occurs, right? Because when resonance occurs, the amplitude will remain high. Okay, so for example, let's say there is a string. Let's say that there is a string that is fixed to two walls. Okay, let's say a string is fixed by nails to two walls. So both the endpoints are fixed. For example, both the endpoints are fixed. Okay, right? Now if on this string by some means we set up some waves. Now how could you set up waves on this string? There are several options. One is you hit it with something that will create a wave pulse, or another option is you can connect over here machines that are called oscillators, right? Okay, it's something like a pin, and this is a machine, so this pin will move up and down, right? So when this moves up and down, it will make the wave generated on this string. Did you understand? Let me repeat what I've said. It's that there are some kind of machines that will vibrate this, okay, that will make this oscillate, so that can create a wave on this string, right? Another way is using something called forks or tuning forks, right? Tuning forks are also instruments right, which can vibrate with a particular frequency. Tuning fork looks like this, right? Okay, you hit it somewhere, then these are called prongs. These prongs will start vibrating. Okay, of course you cannot see it with naked eye, they vibrate very little, but they do vibrate, right? So when you hit it somewhere and bring it close to this, that vibration will pass on to the string or wire, and that will also start vibrating or oscillating. Okay, so these are some of the ways in which you can set up vibrations or oscillations in strings. Now, like I said, that if you want the amplitude to remain high, it is necessary that resonance occurs, that is, the frequency of this oscillating thing, okay, which is called the natural frequency, should be equal to the driving frequency or driving force frequency, right? Okay, for example, suppose the natural frequency of oscillation of this string is, let's say, 500 Hertz. Then the tuning fork, let's say you are using a tuning fork. The tuning fork that you are going to be using should also have a frequency equal to 500 or at least very close to it. 499 will also be good enough. I hope you understand what I'm saying. But if it's 300 Hertz, then that's very far. So in such a case, resonance is not going to occur, right? But if it's, let's say, 499, or even better, let's say it's exactly 500, just like this is exactly 500, then the resonance will occur and amplitude will be very high. Did you understand this so far? Okay. Rohan, you are saying like solenoid. I think you have misunderstood something. Solenoid is a completely different animal. Okay, I am saying animal. What I mean is it's a completely different device, right? It has nothing to do with all this. Okay? Where? Okay, let's continue. So, what is the natural frequency of this string? Right? Is it 500? Is it 700? Is it 120 hertz? What is it? How can we find natural frequency of the string? Okay, how can we find natural frequency of the string? That's what we are going to discuss. First of all, we will take a mathematical treatment, and then I will definitely explain what's going on. Okay, so let's start. So write it: superposition of two waves traveling in opposite direction on a string. Okay. Right. So hopefully you have understood the title. It's saying that on one string there is a wave traveling in this direction. So let's say it's not just one wave pulse, okay, but let's say a wave train. Okay, there is a wave traveling in one direction, and there is also a wave traveling in opposite direction. Okay, let's say. So when these two will superpose, or they will come together at one point, okay, obviously these will continuously be flowing. Again, I am saying wave train. Both of these are wave train, right? They are continuously being generated somehow. Okay, so in this situation, the one that is going towards the positive x side can be written as y equal to a sine kx minus omega t, correct? This is the one that is traveling towards the positive side. Okay, then the one that is traveling towards the negative side can be written as this. Yes or no? Okay, here of course I am using a simple case, right? We have made several assumptions. Have a look. Do you realize both have same amplitude? The way I have written A and A, right? So we are going to add or superpose two waves with same amplitude. Is that okay or not okay? Right? For the K is K, that is, I have not written K1 and K2. What I mean to say is that their K's are same. If K's are same, then lambdas are also same. Is that clear? Because K is equal to 2 pi by lambda. Clear or not clear? Clear or not clear? Okay. Third thing. Omega is also same. That is, frequencies are same. The waves that are generated from their sources, respective sources, their frequencies are also same. Okay. So now if we do addition of these waves, so basically we are talking about a very specific case. A more general case is like this, but that is very difficult to handle. Okay, and it will not explain what we are going to talk about here. That's why we are taking this case, which is what happens on a string that is fixed at both the ends. Okay, so let's say it's like this. Now, once you have it this way, let's add. So by superposition principle, for any point at time t, right? And let's say somewhere there is origin. Let's say here is origin on left side, x equal to 0, and this would be where x is equal to L. I hope that makes sense. Okay, where L is the length of that string, suppose. Okay, like that. So let's add y equal to y1 plus y2. This is the superposition principle, right? So a bit of math coming your way. A common, sine kx minus omega t plus sine kx plus omega t. Okay, let me just do one thing. Whether you add this way or the other way, it doesn't make a difference, right? So I am writing kx plus omega t first and kx minus omega t next. Yes, they were, of course. So, what do we have here? Therefore, y is equal to, I'm sure math students would easily recognize this. It's a well-known trigonometry formula. For biology students, I'm writing the formula here. The formula is as follows. Sine of A plus sine of B is equal to 2 sine A plus B by 2 cos A minus B by 2. Okay, this is a formula that you might have to memorize. Okay, sine A plus sine B will be 2 sine A plus B by 2 cos A minus B by 2. So let's compare and use. This is the first angle A, second angle B, right? So A outside the bracket as it was now. Formula 2 sine A plus B. A plus B, add. So do you realize you get 2kx? When you add the angles, you get 2kx divided by 2. By 2 here, this is the 2. Cos. Now subtract. So this minus this, right? So let me just clarify that here. A minus B will become kx plus omega t minus kx minus omega t, right? A minus B. Open the bracket, so the sign will change, right? So kx cancel and this becomes 2 omega. Okay, everyone understood this step using these things? I hope now you all will really understand that why mathematics is so necessary or so important for physics, right? As you can see in the last 2 chapters, we have been using trigonometry again and again and again, right? Okay. Anyways, let's continue further. So y equal to 2 into A sine 2 to cancel kx. Again 2 to cancel cos omega t. So this is an equation that we have got. Right? This is the equation that we have got. Right? Now we know that when two waves superimpose or superpose, the result is also a wave. Right? Okay, this is like fairly simple idea because like, this is what we have been doing. Addition of two velocities is a velocity, isn't it? Subtraction of two velocities is a velocity. Correct or not? Like that, addition of two waves is going to be a wave pattern. Right? Okay, that's what we have in all superposition principles. Isn't it? I hope you all remember that. Addition of two forces. What is this going to be? Addition of two forces is energy, isn't it? Yes or no? Addition of two forces is energy. Correct or not correct? Addition of two forces is energy. Yes or no? Okay, some of you are saying yes. I hope you are joking just like I am joking. This is nonsense of the highest order, right? Addition of two forces is always going to be a force. So just like that, when two waves combine with each other, what we are getting must be a wave. So this is an equation of a wave. This equation is of a wave. Right? But you see, this one doesn't at all look like this one. Yes or no? I mean, there is kx, there is omega t, fine, but it's not like this in one bracket. Correct? It's not like this in one bracket. On the other hand, what we are seeing is, if you just ignore this part for a moment, we are getting cos omega t. Do you remember in SHM? In SHM, we used to get things like y equal to a sin omega t or that type. Yes or no? Correct? Okay, and in waves that we have studied so far, we are getting this pattern or this pattern, right? But here x is separate and omega is separate, right? Okay, x, kx, omega t, they are separate now. Clear? So this is of course equation of a wave. There is no doubt about it. But if you will modify it, I mean, if you take this part together, okay. Take this part together and write it as a dash. Okay, so let 2a sin kx be equal to a dash. Then y is equal to a dash cos omega t. Do you realize that this is nothing but equation of SHM? Do you realize that this is nothing but equation of simple harmonic motion? Okay, so what's happening here? Is this equation of a wave or is this simple harmonic motions equation, right? We have a problem. Let's solve that out. You see, what is happening over here? Listen to this very carefully. What is happening is that a wave is traveling in this direction. Okay, that's this one, y2. And the first one is traveling in this direction. So when both the waves combine with each other, that is when they superpose, their traveling character is lost. I repeat, their traveling character is lost. What I mean to say is, you could say that here energy was traveling in this direction because wave was traveling in that direction. Here the energy was traveling in this direction, right? But now when both the waves are on the same string, so energy is going this way also and energy is going this way. So ultimately it's like energy is going nowhere. Did you understand? It's like energy is going nowhere. Did you understand or not? Okay, I hope that was not tough to understand. Energy again behaves like money, remember. You give your friend 10 rupees, your friend gives you 10 rupees. Well, energy has been transferred, but the effects have been nullified, right? Effects have been cancelled. What that means is, you can also say that no energy was transferred, right? You can also say that no energy was transferred. So basically, this kind of equation of a wave, where two waves which were traveling in opposite direction like this, okay, they result in a different type of wave where energy is not transferred anywhere. I repeat, they result in a different type of wave where energy is not transferred anywhere. This kind of equation of a wave or this kind of wave is called a standing wave. Okay, this is called a standing wave. If you remember, when we wrote this type of equation at start, with it we wrote the following: equation of a transverse wave traveling in positive x direction. Didn't we? Do you remember that? When we wrote this kind of equation for the first time, we wrote that this is equation of a transverse wave traveling in the positive x direction. On the other hand, now I am saying that this is equation of which kind of wave? A standing wave. Standing wave, that is, it just stands. It's not going there, it's not going there, it's not going in any direction. Did you understand? Did you understand? Okay, now why is it not going in any direction? Again, let me go through it. It's that energy is going that way, energy is also going that way. So net effect is that energy isn't going anywhere. Right? Net effect is that energy isn't going anywhere. Hence the name standing. Another name for this is stationary wave. What's the name? Stationary wave. Right? I'm sure you understood that name also. Okay, names are clear? Right, very good. Okay. Now, what's the SHM thing here? Let's discuss about that. Okay, after having named this thing, let's talk about the SHM part. So, what is happening here? Listen to this carefully. What is happening here is that when we write the equation in this form, we realize that SHM is going on. So, some facts become absolutely clear. Number one, all particles of string or medium, all particles of string or you can also write medium are doing SHM. Okay, there is no doubt about that. This is always true anyways, isn't it? Even if a traveling wave is going, then also particles are doing SHM, right? So I hope this sentence doesn't surprise you. Okay? Waves are not cancelled. Again, also their effects are not cancelled. Let me be very clear. The question is that are waves cancelled? What do cancelled waves look like? They look like this. Cancelled waves look like this. What does that mean? Suppose one equation is something like this. And second equation is, don't write this everyone, this is just for answering that question, is this. Let's say these are two waves going on the same string. Let's say these are two waves going on the same string. Then what do you think is y1 plus y2? What do you think is y1 plus y2? Of course, 0 not just at one point. You understand what I am saying? 0 at every point. 0 at every point, right? You can put any value of x, you can put any value of t. y1 plus y2 will always be 0. That is called cancelled waves. So what will happen if there are two such waves going on the same string? See, they are going. Do you see them? They are going. Okay? That is what is called cancelled waves. Right? Where the wave pattern is completely lost, there is nothing going on here. But the equations that we have added and we have got this. This does not mean y is 0 everywhere. I hope you realize. What I said, you misunderstood this. I said that energy transfer is cancelled because it's just like 10 goes that way, then 10 goes the other way. So how much energy is transferred or how much energy goes from this side to that side? 0, because ultimately whatever is going there, the same is coming back. Clear? Energy is not transferred. The waves are still there. Right? Okay. Fine, let's continue. So I was saying that all particles of string are doing SHM. That's not a surprise. Right? Even in a traveling wave, hopefully you remember that all particles try to copy the source, and when they do that, they will oscillate, they will do SHM. Okay? Second. Now here comes the interesting feature. But their amplitudes are not equal. But their amplitudes of oscillations are not equal to each other. Okay, and put in bracket, unlike traveling wave. Unlike traveling wave. What do I mean? First of all, let's look at this equation. So we are getting an equation y equal to a dash cos omega t here. Let's say we're getting an equation y equal to a dash cos omega t, where a dash is like amplitude. I hope you can compare it with the equation of SHM, right? Do you realize that a dash is going to be the amplitude? Yes or no? If this is equation of SHM, a dash is amplitude. Correct or not correct? Okay. Now, so how much is this a dash? So this a dash, we have taken a dash as 2a sin kx. We have taken a dash as 2a sin kx. What does this mean? This means that a dash depends somehow on x. Yes or no? This means that a dash depends somehow on x. Clear? Clear or not clear? Because if you put different values of x, then sine may take different values. If sine is taking different values, a dash will have a different value. So read this. So all particles are doing SHM, very good. But their amplitudes are not equal to each other. Did you understand? Amplitudes are not equal to each other. That is, every particle does not have same amplitude. Is it clear or not clear? What's the reason again? Suppose here is the string starting at x equal to 0. So as you go towards the right side, do you understand that x coordinate will change? If x coordinate will change, amplitude will also change. Got it? Okay. Right. So some points will have more amplitude and some points will have less amplitude. Right? Some points will have more amplitude, but some points will have less amplitude. So now, right now, let's focus on the points that have zero amplitude. Okay, for the time being, let's look at those points that will have zero amplitude. I am erasing the left part of the board. Okay, point number 3. Nodes. Okay, point number 3, nodes. Okay, what are nodes? Nodes are points with zero amplitude. Nodes are points with zero amplitude. That is a dash equal to 0. That is a dash equal to 0. Okay, definition clear? Nodes are points with zero amplitude in case of stationary waves. In case of stationary waves, right? Okay, so a dash is equal to 0, right? So if a dash is 0, let's put it here and do a bit of math. Then do you realize that we have it like this, and that would mean sine kx is 0. Clear or not clear? Right? Simple bit of math. 2a is divided on that side. Now, which angle's sine is 0? Okay, we go to unit circle. Sine 0, 0, isn't it? Then over here for 180 or pi, it's 0. Correct or not? Do you remember? Because sine is the y coordinate of this point, right? Clear? So here and here, 0, pi, 2 pi, 3 pi, 4 pi, like that. Did you get it? Did you get it or not? 0 pi, 2 pi, 3 pi, 4 pi, etc., etc. Okay, math students very well know this. So in general, do you realize you can write n pi, where n is integer, Do you realize you can write n pi? No covered query? What are 0, 1, 2, 3, 4, 5, 6, 7, minus 1, minus 2, all these are what? Integers, right? Okay? So therefore, I can write that this will happen if the angle, this is the angle, is equal to n pi where n is integer. Okay or not okay? This is equal to n pi if where n is integer. Got it? If you don't like this, remember, I have another way. You can write it as follows. You can write it as follows. Soon you will understand the pattern. Did you get the pattern? 0. 0 means 0 pi. Yes or no? 0 into pi is 0. 0 pi, 1 pi, 2 pi, 3 pi, 4 pi, like that. So ultimately, if we will continue from here, k is 2 pi by lambda, x equal to n pi. Therefore, pi is cancelled and x equal to n lambda by 2. Understood? X equal to n lambda by 2. So we are saying, listen to this carefully. We are saying that nodes are those points with 0 amplitude, right? Okay? Nodes are those points with 0 amplitude. And where are the nodes? If x is equal to n lambda by 2. Right? If x is equal to n lambda by 2. So, x equal to n lambda by 2, again n is integer. This is where the nodes are going to be. What does that mean? Suppose I put n is 0. Remember, integer means you can put 0. Right? 0 is an integer. So 0. Fine. So here is a node. Where we know that. We know that. Why? Because we are actually talking about a string that is fixed on both ends. You understand what I am saying? We are actually talking about a string that is fixed on both ends. Yes or no? Node means what? Again, amplitude is 0. Now think about it. If amplitude is 0, have a look at this equation. If a dash itself is 0, is 0, then this whole thing is always 0. Correct? What does that mean? Can something oscillate with 0 amplitude? What does it mean? If I say that this duster oscillates with 0 amplitude, what does that mean? If I say that this duster oscillates with 0 amplitude, what would it mean? Don't raise hand, give answer. What would it mean? If I would say that this duster is oscillating with 0 amplitude, what does it mean? Gracie, I am talking about duster. I am not even talking about waves. Yes, it means duster is stationary. Why? Because its displacement is always 0, right? You can see that here. Its displacement from the mean position is always 0, right? I hope you understand what I am saying. It's not going anywhere because its amplitude is 0, right? So its displacement will also be 0 always. Understood? So this point is fixed or stationary, like I said earlier. Right? This point, the node is fixed or stationary. Clear? Clear or not clear? Okay, fine. Then where will be the next node? This is one node. Fine, very good. Where is the next node? Here we put n equal to 0. Now we will put n equal to 1. So 1 lambda by 2. So at some distance, which is equal to half of wavelength. At some distance, which is equal to half of wavelength, we are going to have one more node. Did you understand? we're going to have one more node. Okay, let me just leave a little bit more space, right? So I'm not changing anything, don't worry. Okay, I'm just leaving a little bit more space, that's it. Right? So here is the second node. Right, then one more node will be when we put n equal to 2 here. Right? So to cancel lambda means one more time lambda by 2 from here. Did you understand? Did you understand or not? Everyone? Okay. But there is some very interesting fact or a very interesting phenomenon going on here. It is what is happening at this point, at this point, at this point, or at the next node or at the next node. It is that when the two waves are coming together, they are superposing when they move from here to there, right, left to right, right to left. At this point, by superposition principle, we are always getting y1 plus y2 equal to 0. Did you understand what I am saying? At this point, by superposition principle, we are always getting y1 plus y2 equal to 0. Okay? Okay or not okay? Same thing here. Same thing here. And further. Understood? Understood or not understood? Okay. So, Gracie, this is what you said is here, right? That's exactly what you said. The waves are cancelling each other, but not at every point. Remember, the waves are cancelling each other, but not at every point, just at the nodes. Did you understand? The waves are cancelling each other, right? Not at every point, but just at the nodes. Fine? Got it? Okay. Another interesting thing. We agree that this point was fixed on the wall with nail. Was this point fixed with anything? I am asking you. Was this point, which is in the middle, somewhere in the row or the string, was this point fixed by anything, by a nail or anything? No. Very good. And still it will not move. I hope you realize that. And still it will not move. Do you remember earlier what I told you about superposition? That it's possible that sometimes two waves will come at the same point and they will cancel each other. Do you remember that? Do you remember? Then I asked you about sound. Correct or not? That is it possible that two sounds come to one point and cancel each other? Well, yes, it is possible just like this. But there is a big condition, big if. Okay, very big if. What is that big if? If you want to get some idea about what that big if, go to the derivation part of this topic. At the start, we did a bit of maths. Isn't it? There we assume that some quantities are same. Do you remember? There we assume some quantities are same for both the waves. Yes or no? Which quantities did we assume are same? Amplitude, frequency, wavelength, and all that. Okay? Yes or no? So, if all those are same, then only what I said can happen, that one sound wave and another sound wave, when they come to one point, they cancel each other. And suppose you put your ear exactly at that point, then even if there are two sound waves reaching your ear, ultimately they are cancelling each other, so nothing will be heard at that point. But yes, if you move a little bit left side, you will hear it. If you move a little bit right side, then also you will hear it. But right at this point, you will not hear it. Did you understand? છે ને જાદુ જેવું છે કે નહીં? Okay, let's hope that everything becomes normal, okay, and you all can come to school and we can conduct experiments, because I can show this not just with sound, I can show this to you even with light. The light comes from this side, light comes from this side, they cancel each other and you get darkness. Okay. Well, never mind. Let's continue with the discussion. So I was saying that we have nodes like this, right? We have nodes like this. This very thing allows us to decide one more condition. See, do you remember that we were actually talking about a string that is tied or fixed at both ends? Yes or no? Can you see till here? Can you see that? Okay, just barely. So, do you realize that this last point of the string should also be a node? Yes or no? The last point of the string should also be a node. Yes or no? Okay? Because that's fixed. Fixed point can't move. That should be a node. Now, so what that means is, for all the discussion to be true, for a string tied at both ends, okay, I am erasing point 1 and point 2 from here, okay, but I leave the diagram as it is, we need it. So we can say for a string rigidly tied at both ends, x equal to L should be a node. Did you understand this sentence, everyone? X equal to L should be a node. Why x equal to L? If this is x equal to 0, then all the way till there, this is length of string, isn't it? Okay or not okay? Right? So x equal to L should be node. So let's use that here. So L is equal to n lambda by 2, or lambda is equal to 2L by n. So what these relations are telling you is that for a string that is rigidly tied at both ends, whatever discussions that we have done about standing waves, whatever discussions we have done about standing or stationary waves, they can only be true if this is correct. Did you understand? Where n is some integer, okay? N is some integer. Of course not 0, because you cannot divide this by 0. Is that clear? Okay, n will be integer but n will not be 0. Understood? Understood or not understood? Can we find number of nodes in string? Yes, Raj, we can find it. Very easy thing. Suppose, let's say that standing waves are there in a string. Okay? Suppose there are standing waves in a string. And let's say that length of the string is 1 meter. Suppose. Okay, Raj, I am answering your question. Let's say that length is 1 meter. The question is, how many nodes are there on a string? Can we find that? So I am giving an example. Suppose length of string is 1 meter and wavelength of the wave is 10 centimeter. Suppose length of string is 1 meter and wavelength of the string is 10 centimeter. Then there are two ways to find it. Two ways to find how many nodes are there. right? One very simple way, distance between two consecutive nodes. How much distance between these two consecutive nodes? Lambda by 2. So lambda by 2 means 5 centimeter. Yes or no? Yes or no? So like this, you can say that there are 5 centimeter, 5 centimeter, 5 centimeter, 20 such gaps. Yes or no? 20 gaps. Clear? 20 gaps, everyone. Is that clear or not clear? So there are 21 nodes. Did you understand? There are 21 nodes. If there are 20 gaps, there would be 21 nodes. Okay? If there are 20 gaps, there are 21 nodes. Fine? Method clear? There is one more way. You can use this formula. Put L's value, put lambda's value. Okay, I'm doing it like that also. 1 is equal to n, lambda is 0.1 upon 2. So this will give you n is equal to 20. But what is meaning of n equal to 20? Have a look. You are starting at n equal to 0 over here, isn't it? To get x equal to 0, you get n equal to 0. Correct or not? This is n equal to 0. So like that 1, 2, 3 up to 20. So 0 to 20 nodes are there. How many nodes? 0 to 20. Right? Of course, Mavi, that's because of counting, right? Or this is the other method. Understood? 0 to 20 nodes. Now 0 to 20 nodes actually means 21 nodes. Correct? You can count that if you want. Okay, so that's how you can find out number of nodes. Right? Two ways to do it. Fine. So we still have more points to write. Okay, we are done with nodes actually. We will now go to the second part, the next part, anti-nodes. Okay, opposite of this. Alright? So we will continue in the next lecture. Goodbye.